the technique we're looking at is a general option to somehow slightly speed up things. To a certain extent, you can ask yourself, how much can you further speed up the computation of edit distance? We've seen with this assumption that you're only interested in the small values, you can do something. If you're interested in the general problem, any kind of strings, and you want the precise answer, how much can you improve upon this textbook undergrad algorithm that we've looked at, the dynamic programming one? We'll see one dimension to improve the space usage specifically, but keep the running time unchanged next time. Another option is to somehow play other tricks and try to speed up the general algorithm while not trying to avoid essentially filling the entire table. And what this exhaustive tabulation method is, can in essence be explained with a slightly different problem. Suppose we multiply Boolean matrices. Now, this is simultaneously a good and a bad example. It's a bad example because I'm well aware that there's more efficient matrix multiplication algorithms specifically. But let's ignore that. So all of these fancy divide and conquer variants and the tweaks and twists on those that try to get this exponent down. If I start with an n by n matrix A and an n by n matrix B, and I'm interested in their product, the basic method would need cubic time because it has to compute all these little products. Every entry in the result is a dot product of a row and a column. And in a stupid way, the best we can do is spend linear time for each entry. Now, again, ignore the divide and conquer methods to speed this up, which are essentially playing with that we're doing multiplications in a specific structure on numbers where I also have a subtraction. This is only possible because it's numbers I can compute with. You can modify the problem to not be standard multiplication, but some other combination of the entries, and then we don't know anything better, substantially better than this n cubed. But this is really, I don't want to get into this really. What I want to show you is something entirely different. And so please just forget about what you learned, that you can do this better. What can we do without any special knowledge about the multiplication, but about the fact that it's Boolean matrices, that the entries are really small? And Boolean is just the extreme case of that. What you can do is split the matrices into small submatrices. I'm going to assign these a size. So this is a T by T submatrix, and we'll pick T later. It's supposed to be square. So that means also this product matrix consists of these little squares. Let me be more smart and just copy it. And now, by virtue of how matrix multiplication works, if I'm computing this submatrix of the result, I'm essentially computing products of submatrices of the input and adding them up. Okay, element-wise addition. What does that help? Well, because these are Boolean matrices, I can make T small enough so that there's not too many different little matrices. There's only 2 to the T times T, 2 to the T squared, different little matrices. Just because they're all 0, 1s, that's the only option. Okay? So if I take 2 of these and take their product, there's also going to be just that squared many options for the output. So if I pick my T small enough, and I need a really tiny T, fair enough, but if I pick my T small enough, I can pre-compute not just all combinations of submatrices from A and B, but all thinkable products of tiny submatrices. And again, this looks bad, but if T is small enough, that's actually negligible. And then every operation here, every product is in constant time on a word RAM, because I can use the indirect address to jump into the lookup table by just taking the entries here and treating them as a number. Okay. I'll try to make this a bit more clear next time again. But the benefit is, instead of having an operation that used to be T cubed operations for doing these little products, we replace that by a constant operation. And so by choosing the right T, we can get the overall cost down, divided by some power of logarithm, log n. There's a power there that I forget. And that same trick we're going to try to apply to edit distance.